Welcome to this lecture. This is the fourth lecture of week 1. In the previous lectures, we have introduced the concept of LP spaces on measure spaces, and on top of that we have discussed properties of the P norm. We have justified calling it a norm and by showing the important properties of the norm. Moreover, since LP space forms now a norm linear space, we have a natural distance function given by the norm. This distance function or the metric yields a topology on these LP spaces. In this lecture, we are going to be talking about convergences in terms of this distance or the metric. So, without further delay, let us move on to the slides. So, let us set up the notation once more. We are going to be talking about this P norm, and as we have already seen, this P norm gives us a natural distance, which is that given any two functions in LP, there is this natural distance given by P norm of f minus g. Now, this allows us to consider convergences for measurable functions, and in the special cases of probability measures, we end up with random variables, and therefore we can talk about convergences of random variables in this LP space sense. So, we are going to be continuing with the notations that we have been so far using. So, let us set up the main terminology. First, let us consider the notion of convergence in LP. We say that a sequence of functions fn in this LP space converges in LP to another element in LP if f minus fn, the P norm of that, goes to 0 as n goes to infinity. Now, this concept can be restated as we have seen earlier for random variables also, and let us restate it. So, this is now convergence in LP with the probability measures. We say that a sequence of random variables xn in LP converges in LP to a random variable x in LP if the P norm of x minus xn, which is nothing but the pth root of the pth absolute moment of x minus xn, that should go to 0 as n goes to infinity. Now, as you can see that this is equivalent to the fact that just the pth absolute moment of x minus fn should go to 0 as n goes to infinity, and therefore we can visualize it as a convergence in the pth mean, or as it is said, in the pth moment. Now, we will typically call it in terms of the pth moment when we are dealing with random variables. Whenever we are dealing with generally measurable functions, we are going to be calling it a convergence in LP, but both notions are the same. Now, we introduce notations to talk about this type of convergences. We shall write fn converges to f, but with a superscript like on the arrow with LP here. For random variables, the similar notation we will have LP on top of the arrow to denote these convergences. Now, in what follows, we are going to be focusing on results specifically either on LP of mu or LP of P, but not both. Note that results which we have stated for LP of mu, that is for any general measure mu, also applies to any probability measure P, and therefore it will hold for LP of P. But some of the results may not be true the other way, meaning if we prove some results for LP of P considering it's a probability measure, then some of the results might not hold for general measures. We have already seen example of such a result when we have shown that LP for P greater than 1 contained in L1 when you are dealing with a probability measure. In case of finite measures, the result continues to hold, but may not be true if you are dealing with an infinite measure. So, whenever you see some result proved for LP of P, be careful before assuming that it also holds for a general measure. We now move on and discuss convergence properties. First of all, we have already seen that if a random variable is in LQ, a higher q than p, then x also is in the lower integrability space LP. Now that result also implies this next convergence statement, that if you choose any p and q in this range, that between 1 and infinity, and p is less than q, then convergence in LQ, the higher moment, implies convergence in the lower moment. To see this, you just recall that there is this interesting inequality that we have proved in the previous lecture, that was in remark 3, that the p norm of x minus xn is dominated by the q norm of x minus xn. This is true whenever p is less than q, but then the higher moment, that is in terms of the q norm of x minus xn, that goes to 0 by the hypothesis, and therefore x minus xn, the p norm of that must also go to 0, and hence we will get the required convergence as required. Now as an exercise, you can try to show that the other direction is not true, meaning that you choose p and q like this, but assume the convergence in LP only. Try to show by an example that it may not be converging in LQ. Construct explicitly the sequence of random variables such that this statement is true in LP but not in LQ. We are now going to be restating the dominated convergence theorem that we have stated earlier in proposition 2. So this is now proposition 8. So take a sequence of functions f1, f2, fn and so on, and a limit function f. Suppose this convergence holds mu almost everywhere. If there exists a function g in LP such that modulus of fn is dominated by g, then all these functions f, f1, f2 and so on must also be in LP. Moreover, the convergence should hold in LP. So the DCT is now being restated, and the integrability condition is now in terms of the LP integrability. So of course you can restate this condition in terms of random variables, but we are not going to be doing that. We are now familiar with the notion that if you prove something for general measure spaces, this also applies to probability measures. So any result that is proved in general for measurable functions also applies to random variables. But as a practice, you can try to write down this statement for random variables on your own. Now we establish a very important approximation result on LP. This is approximation by simple functions. Remember that for a measurable function we have seen such approximation results, but in the almost everywhere situation. The approximation require the use of the LP norm or the metric that is associated to the LP norm. So we show these approximation results using the LP distances. Start with a function f in LP. Then for any epsilon positive, the statement says that we can construct a simple function g such that f minus g, the p norm of that must be less than epsilon. Moreover, this g that we are stating here can be chosen with further additional properties such as modulus of g should be less or equals to modulus of f, and g must be finite valued. Here let me clarify the term finite valued. Whenever we are talking about simple functions, it is a finite sum of indicator functions. Now whenever we are talking about finite valued, we mean that these functions do not take the values plus or minus infinity. This approximation by simple functions, this statement can also be restated in following alternative variants. So before proving this, we restate these versions first. Consider the class of simple functions which are already in LP. So there might be some simple functions which are not in LP. Be careful with those. So continue with these simple functions which are already inside LP. Then the closure of such a class, by closure we mean that we are using the topology in LP. So that closure in LP turns out to be the whole space itself. So this is the approximation by simple functions. So therefore by limiting operations we can approximate any LP functions. So, therefore, this closure is the whole space itself. Another way to state the same result is that the simple functions in LP are dense in LP. We can also state it in terms of approximations by sequences. Start with a function f in LP, then there exists a sequence of finite valued simple functions given by Gn such that Gn converges to f in the LP sense. Moreover, modulus of Gn must be less or equals to modulus of f for all n. Since we have restated the original result in alternative forms, let us now move on and look at the proof of this. Since f is measurable, first of all we can construct a sequence of finite valued simple functions such that Gn converges to f in the pointwise sense. Moreover, we can also ensure that modulus of G should be less than modulus of f. Here there is a minor typo. This will be corrected in the final lecture notes supplied to you. Since the limit function f is in LP, by this domination we will claim that Gn must also be in LP. So, therefore, the sequence of simple functions that we are dealing with here are already in LP. Now, observe that if you look at modulus of f minus Gn, that can be dominated by modulus of f plus modulus of Gn, but since Gn's are less than modulus of f, we end up with 2 times modulus of f as an upper bound for modulus of f minus Gn. But f is already in LP and it immediately follows that 2 times modulus of f must also be in LP, and hence by applying DCT we will claim that f minus Gn must now converge in the LP sense to 0. Another way to state this is that Gn converges to f in the LP to the function f. Now, in particular, for any epsilon positive, we can find a natural number n such that f minus Gn, the p norm of that, should be less than epsilon. This is following from the fact that we have shown that the sequence of values f minus Gn p norm of that sequence of values converges to 0. Therefore, given any epsilon positive, we can choose a large enough integer n such that nth term onwards the terms are smaller than epsilon, and hence this G subscript capital N is our choice for a finite valued simple function which is also in LP. This completes the proof. We now move forward and introduce another related concept to convergences. This is the notion of Cauchy sequences in LP, and as we shall see, these Cauchy sequences in LP plays a very important role. Let us recall the definition. We say that a sequence Fn in LP is Cauchy if given any epsilon positive, there exists a natural number n such that all terms after that n onwards are closed by epsilon. All n and m, or small n and small m, the corresponding functions fn and fm must be closed in LP distances, closure by this epsilon distance. This is the notion of Cauchy sequences. We have already seen such similar definitions in the real line, and in fact in any metric space such as the real line or the LP space that we have been discussing, all convergent sequences are Cauchy. This is an important property that convergent sequences carry. But conversely, we need to recall that Cauchy sequences in R are convergent. This is a very important equivalence that is established on the real line. Remember again, in any metric space all convergent sequences are Cauchy, but for the converse direction, starting with Cauchy sequences and going to convergent sequences works in the real line. What we are going to be discussing is a similar property in the case of LP spaces. And remember, from Cauchy sequences to convergent sequences, if we can show such a implication, we get the completeness of the space. For example, on the real line, if you manage to show that Cauchy sequences are convergent, then we end up having the completeness of R. What we are going to discuss is a similar property for the LP spaces. Before that, we recall an important result from basic measure theory. This is the Bodel-Cantilli lemma, first half of it. In a later lecture, we are going to be seeing the second half of it. So, we are going to be working with this measure space and choosing this sequence of sets coming from the sigma field. Suppose this sequence of sets satisfy this property that sum of their sizes under the measure mu should be finite, then it follows that lim sup of an must have 0 measure under the measure mu. This is the Bodel-Cantilli lemma, first half. This is also an important result as you see in probability theory, where a measure mu is replaced by a probability measure. As a consequence of this, we are going to be obtaining an important technical lemma. Suppose I have a sequence of functions fn in LP such that the n plus 1th function and the nth functions are closured in P norm by this distance 4 to the power minus n for all n. Then the claim is that the sequence of function must converge in the almost everywhere sense. To see this, we start by looking at the sets n equal to 1, 2 and so on, defined by this set of points where these functions differ by more than 2 power minus n distance. This is point-wise distances that we are looking at. Now remember, according to the notation that we adopt, we are going to be removing these small omegas and simply rewriting this inequality here. This is again another shorthand description of the sets an that we are going to be using. Now the Markov inequality that we have just talked about gives us that the size of the sets under the measure mu can be dominated by the pth power of this norm and with this appropriate scaling. This is the application of Markov's inequality. But since we have chosen these sets in this familiar manner and these sequence of functions satisfy this 4 power minus n distance, so raised to the power p you get minus n to the power p, and finally the size of the sets an must be dominated by 2 power minus np. This is a very standard manipulation that we have performed, and as a consequence of that, sum of the sizes of the sets turns out to be finite since we are working with p between 1 and infinity. Now it is the application of Bodel-Cantilli lemma first half, and we will immediately claim that lim sup of these sets that we are considering must have 0 measure. Now while dealing with integrations, we have stated earlier also that we are going to be ignoring these sets of measure 0. So on the complement of this lim sup set that we see here, we are going to be doing our analysis. Now on the complement, by the description of the sets an, we conclude that for large n of n, we will now continue to have the upper bound given by this. Remember, the sets an were given by the other side of the inequality, and lim sup an complement essentially says that after a stage onwards you are going to be having the other side of the inequality. Therefore, for all large n you end up with this upper bound which is pretty short, which is 2 power minus n, and hence as a consequence of this we get the pointwise convergence of the sequence fn omega. This fn omega is a real sequence, and this bound actually implies the Cauchy property. By the completeness you immediately have the convergence, and hence what we have established is that on the complement of this null set, which is the complement of this lim sup, on this complement we have the pointwise convergence of the function values. Now on the set of measure 0, we do not really care about the limit function values. So therefore we essentially conclude that outside this null set anyway we have shown the convergence. So therefore this sequence of functions converges almost everywhere. So therefore this technical lemma is proved that as soon as this sequence of functions fn satisfy the relation that fn plus 1 minus fn in p norm is smaller than 4 to the power minus n, then this will converge in the almost everywhere sense also. Now we are going to be commenting on a specific part of this proof, that we have not really explicitly identified the limit function here. What we have done is that on the complement of the null set we have essentially identified the limit, but haven't really identified the whole limit function on the whole domain. But we can do it very easily as done in the following expressions. So what we do, we state this function on the domain omega with real numbers as its values given by this, that on the complement of this lim subset we continue to take the limit values as already justified, and on the set of measure 0, which is the lim sup, we will just set it to be 0. That will completely describe this limit function, and as we can see, it is a very standard easy verification that this limit function f that we have been claiming, this is actually a measurable function, and this almost everywhere convergence will hold. Now here of course we need to comment that instead of the value 0, we could also use any other known measurable functions, and that will also work as a limit function. But we have to keep on the complement of the null set the value given by the limit function. Only on the null set we can change the values according to our wish coming from any measurable function. For example, we have used the constant function 0 here. Now combining all these results that we have seen so far, we now come to a very important structural property of LP spaces. So far what we have already observed is that LP spaces together with the norm forms a normed linear space. But with this property of completeness that we have been discussing so far, we claim that all the Cauchy sequences in LP are convergent, and as a consequence of that what we end up having is that this nonlinear space LP are complete. So let us establish this result. So we have to start off with Cauchy sequences in LP and show that they are convergent. But before we prove this, let us make some comments about this result. So what we have is that these LP spaces are nonlinear spaces, and this previous theorem is saying that these spaces must be complete. So LP spaces are complete normed linear spaces which are nothing but Banach spaces. So therefore we have very special structure of these LP spaces which turn out to be Banach spaces. Now we go on into the proof, and here we shall see the application of the technical lemma that we have established earlier. We start with a Cauchy sequence Fn. Now since it is given to be Cauchy with any choice such as 1 by 4, we can get a number capital N1 such that all the terms after this now number N1 must be closer to each other by this distance. Now as soon as we obtain this N1, we set the first function G1 to be f of N1. Likewise we continue, and what we do is that we now choose a smaller number which is 4 to the power minus 2, and accordingly we will be obtaining a number N2 so that all the subsequent terms are closer to each other by this rate. And without loss of generality, what we can do, we can choose this N2 to be greater than N1. With those choices we now set G2 to be f of N2. Proceeding likewise, once we have obtained the first k many functions G1, G2, Gk, we have to explain how to get the next function. To do that, first we find nk plus 1 greater than nk such that all the subsequent functions after that stage onwards must be closer to each other by this distance. And as soon as you obtain such a number nk, you set gk plus 1 to be that function. Therefore this way we have managed to construct a subsequence of the original functions itself. Remember, gk's are special choices of the functions from the original sequence, and therefore gk's are actually a subsequence of the original sequence. Now this subsequence has been constructed with the property that the subsequent distances between all these successive functions is less than 4 to the power minus n. That is how we have constructed this subsequence. By this earlier lemma, what we have is that this sequence of functions converges mu almost everywhere to a limit function, and therefore we just give it a name, call it g. Therefore, we have a subsequence which converges almost everywhere to a measurable function g. We first claim that this limit function must be in LP, and finally we are going to be showing that the original sequence itself must converge to this limit function in the LP sense. So, we have managed to identify the limit function of the original sequence. To establish this, first fix an epsilon positive, then again by the Cauchy property of the original sequence, we can get a number capital N such that successive distances between functions after the nth stage will be less than epsilon to the power 1 by p. In particular, if we choose our nks which are larger than capital N, then replacing the fm by f of nk, we end up with this relation. And here, as we let k going to infinity, fix the capital N, let k go to infinity, we will end up with that the lim inf of these quantities is upper bounded by this epsilon. The only difference from the previous relation to this relation is that we have raised it to the power p, and therefore we have gotten rid of the epsilon to the power 1 by p, and this appears as the epsilon on our left hand side. Now remember, the norm raised to the power p actually is an integral, and therefore here we can apply the Fatou's lemma, push the lim inf inside, and therefore you will get this inequality here. This is an application of the Fatou's lemma. Once you have that, observe that we have already established the pointwise convergence of these subsequences here, and that is nothing but what we denoted by g. So that next expression is an equality, because by identifying the limit, this is a pointwise limit. But then this again can be expressed in terms of the pth power of the p norm between fn minus g, which we now happen to have to be less than epsilon, and in particular fn minus g, p norm of that has to be finite, and therefore it is in LP. Now since this can be made smaller than epsilon for all large capital N, then fn minus g converges to 0 in the LP sense. Therefore, as a whole, what we end up having is that the function g that we have obtained as a limit of subsequences now can be rewritten in this algebraic form as a difference between fn and fn minus g, both of which are LP functions. Since LP is a linear space, g must also be in LP. And finally, once we have established fn minus g converges to 0 in the LP, we just rewrite that relation and end up having that the original sequence fn itself converges to g in the LP sense, and therefore this completes the proof. The final statement that we are going to be talking about in this lecture is this important result, that what is the relation between LP convergences and almost everywhere convergences. In the DCT, as we have seen, almost everywhere convergences with some integrability condition implies the LP in convergences. On the other hand, we are going to be seeing this important relation from LP convergences to almost everywhere convergences, but only through a subsequence. So the results taste like this: we take a LP convergent sequence, then we can get a subsequence which converges to the limit function in the almost everywhere sense. To see this, start with the convergent sequence. Now since this is convergent, this is Cauchy, and with the type of arguments that we have been doing earlier, we can construct a subsequence such that the successive functions are closer to each other in the p norm by 4 to the power minus k distance for every k. And therefore, by our earlier technical lemma, this specific subsequence that we construct converges almost everywhere, and let us call this limit function g. As we have seen earlier, this limit function, this convergence actually holds also in LP. But observe here that we have started off with the original sequence converging to the limit function f in the LP sense, and therefore as a consequence of that, by considering the uniqueness of the limit, we can check that f and g must match almost everywhere, and therefore as a consequence of this we will immediately get that f of nk, the subsequence, must converge to the limit function f in the almost everywhere sense. Please complete the argument. This is left as an exercise for you. This completes the proof. Okay. So, up to this we have discussed some important properties of LP spaces and proved that LP spaces forms Banach spaces. So, in the next lecture we are going to be talking about spaces related to be LP spaces. We stop here. Thank you.